So, having spoken about GANs, now let us quickly talk about another interesting family of generative models, which is still very widely used today, which are called variational autoencoders. And it's very easy to understand because we've already spoken about autoencoders. And just a quick reminder, if you remember, autoencoders we discussed when we were talking about self-supervised, unsupervised approaches for learning lower dimensional feature representation from unlabeled training data. What we do is we start with our input. X can be an image such as this one. We encode it. We have a network which goes down inside, goes down to Z, and then from there we originally we used models such as linear plus sigmoid. Later we started using deep learning, deeper, fully connected, or later even ReLU and CNNs. And we still use ReLU and CNNs for the VAE. We don't still use transformers to the best of my knowledge. And then usually, we know that Z is usually smaller dimensionality reduction because understanding is compression. And then also because we want our features to capture meaningful factors of variation in data, and data usually lies in a lower dimensional manifold as compared to the original dimensionality of our data. And then I'm sure you remember very clearly, we also then have a decoder which then takes us back to the input image, and we compute the L2 loss between them. Yeah, so we then compute the distance between them. What we want are the input and the output to match. So for a given input we get X dash as output, and then we say that both of you have to be as close as possible, and we penalize if you are not, and that is the loss that you compute. You back propagate through the loss, you train both the decoder and the encoder bits, and after training is done, we throw away the decoder completely. Yeah, so we use the loss. It doesn't use labels because it's self-supervised, and after training we throw away the decoder, so we don't need the decoder anymore. And then if you remember, we said that autoencoders can then also be used because you have your Z, so this is what the autoencoder is giving, and then on top of that you can have like a really small classifier. So you can take your Z, and then from Z you can put a small weight and bias on it, like a small linear layer, and then you can have maybe your 3x1 output, which is then we call this as your classifier layer, right? So on top of your representation, if you're then computing the output, that's your classifier layer as shown here. And autoencoders can be used to reconstruct data, can also learn features to initialize a supervised model, and features capture variations, so factors of variation in training data. Now the question is, can we generate new images from the autoencoder? Yeah, so we are able to generate these features and we have the decoder. So can we generate new features? Can we give it new Z and generate new X hats? The answer is no. Why? Because we do not know how to create Z. Because Z is some latent representation. Z has some distribution, and we do not have control over this distribution. We do not know how to sample from Z, because we might come up with a random vector, but it may not be in the distribution of Z. So the whole question is, how do we know how to sample from Z? Is there a way to know how to sample from Z? And to do this, we came up with the idea of variational autoencoder, which is essentially a probabilistic spin on autoencoders, and basically it will let us sample from the model to generate data. It will tell us how can you sample different Zs, right? So how can you sample from your Z distribution? And the idea is actually really simple. What we want to do is we want to use the same autoencoder, but what we want to do is we want to then essentially enforce an additional loss on our features here. What we want to say is that our Zs that are coming in should come from some known distribution. Let's say from a unit Gaussian, from a normal distribution with 0 mean and 1 standard deviation. And the encoder and decoder networks are also called, recognition or inference and generation networks. So how do we enable that? How do we enforce our Z to, let's say, come from a unit normal distribution, a unit Gaussian distribution? And the idea is to simply minimize the KL divergence. Look up KL divergence, we'll provide in the let's say rabbit holes, but essentially it's the distance between the distribution Z and a Gaussian. So all you're saying is that you have your distribution Z, so you want to minimize the KL divergence between the probability distribution of Z and the probability distribution of this unit Gaussian. So if you do that and enforce that as a loss in addition to our L2 loss that we have on our reconstruction, right? So we have then these two terms in the loss function, and once you're doing this, you're forcing your feature Z to lie on a unit Gaussian. And why are we doing this? We are doing this because scale divergence is a measure of how one probability distribution varies from another. So how are P of X varying as compared to our normal distribution? And once we have enabled this, once we have done this, then we know how to sample from a unit Gaussian, right? And if we know how to sample Z's from here, that means we can sample as many Z1, Z2 we want, and then we do not throw away the decoder, right? We use the decoder, and then the decoder can then generate new samples from us. Now, to do that practically, Kingma and Welling published this seminal paper in 2014. However, I think they got popular. The algorithm itself, the VAE algorithm itself, got popular a little bit later. But the idea here, so this is where the magic happen, and I want you to listen very carefully here. So the only thing you need to remember when thinking about VAEs, of course, it's like your normal autoencoder, but here is where the difference is. Instead of actually just predicting Z, what you predict are mu's and sigmas. You kind of just assume that, okay, I have, let's say, a DL distribution, so a DL dimension distribution. The dimension of my latent space is DL, and I'm gonna have so many mu's, right? So I'll have mu1, mu2, so I have so many dimensions all the way to DL, and then I will have my mu1, mu2 all the way to mu DL. And similarly, I will also have so many sigmas, my sigma 1, sigma 2, and all the way to sigma DL. And this is what I output as the encoder. So I assume that the encoder is outputting this. And on this, I know how to put my KL divergence loss, because the mu's and sigmas make my normal distribution. So I know exactly how to then enforce, how to then compute the KL divergence between this and the unit normal, which I want it to lie on. And this is a differentiable loss, so you can directly plug it in to PyTorch. And during inference, so when we actually train, when we actually then go from the encoder to the decoder, you sample from this. You have your mean and sigma. You sample from it, whatever you've outputted here using your means and sigmas. You sample from that, and then you compute. So your samples are mu1 sigma 1, and epsilon 1 mu2 sigma 2, and epsilon 2. And again, this is differentiable. So you backprop through that, and you can then update your mu's and sigmas. So again, variational autoencoder, same as regular autoencoder. Regular autoencoder, you are not able to sample because the latent space is in a distribution we do not know how to sample from. So we ask the question. Kingma and Welling asked this question in ICLR 2014. How can you sample from a variational autoencoder? So, okay, the latent space, we don't know what distribution it is. Let us know what distribution it is. Force it to lie on a unit Gaussian. How do we do that? Okay, minimize the KL divergence. Okay, how do we get to do that? Okay, output the variational autoencoder, output the encoder. So, of the variational autoencoder, get the encoder to output the mu's and sigmas. And then using those mu's and sigmas, I can generate Z1, Z2, Z3, right? So, I can then do my forward prop. and then I can do my backward prop, and then I can have my encoder and decoder. The encoder learns to output the mu's and sigmas given my input, given my high dimensional input, given my image, and then given these mu's and sigmas, my decoder knows how to reconstruct. So now I can sample. I can now, let's say, sample different latent vectors from my distribution of mu's and sigmas, from my latent distribution, from the distribution that I have made it close to based on the loss. I now know how to sample here, which I did not know in the autoencoder. So I can now sample from here, and thus based on that I can create new images. So again, the encoder is giving us mu's and sigmas, and then those mu's and sigmas we are using to create z1, z2s, right, and the zds, and then we are putting it into the decoder, and we are also minimizing our x and x dash, the L2 between your x and x dash. So if this is your x, this is your x hat, we are minimizing the L2 of that. And it's an implementation detail. You should know this, that in implementation, psi1 is essentially log of 1 plus exponential of this rho 1 to keep it positive. But this is again just a numerical thing, and this is something that we need to take care of when we actually go ahead with the implementation. And now once you have trained your decoder, you can then sample from the distribution, your normal distribution of zeros and of mean 0 and covariance identity. So the covariance matrix is all ones for your Gaussian, and then you can sample from this distribution. And this is again this is so what they did here was they kind of created just two, so the latent representation is just z1 and z2, and now when they kind of sample different z1s and z2s, when they are here they get images that look like this too. When they're here, so once they sample between this different z1s and z2s, the different dimension of z1, z2, you kind of get this kind of an image, right? So this is something that you get on sampling from this distribution, and I highly recommend you kind of check this paper out for more understanding. But the message that I wanted to give you, so like I said, you were varying z1 and z2, and based on that you get this data manifold in 2D which we can visualize. You can also do this with faces, and with faces the two leading dimensions z1 and z2 happen to correlate with the head pose and smile. But again, there is no guarantee what each of those z1s and z2s will. So there's no semantic mapping between the attributes that we're interested in, for example head pose or smile, to z1, z2, but for this there can be another linear mapping which map your semantic attributes to your latent vectors, and then using those latent vectors you can then generate your final output. Meaning you want knobs in your semantic space. So you create a mapping between the knobs in your semantic space to the knobs, the sliders, the knobs in your latent space. And now once you have that, you can then put this here. So now I know how old, how smiley, and then I can then use this Z to use the decoder to then give us the final output. And that's all that there is in variational autoencoders.